In this video, we're going to look at the global winds. The global wind systems is one of the most important aspects that creates world climates. There are many aspects which form ingredients that go into the stew of a global climate, where it might be in New York or Paris or South Africa. What creates that particular climate in that particular place? And of all of them, we know that the amount of insolation that you get from the sun is the number one factor, right? Whether you're in the tropics, you get lots of energy from the sun, or the poles, you get less. That's the number one factor. But the second most important factor of all is the global winds. The global winds are going to take that tropical energy, they're going to move that away from the tropics towards the poles, towards the mid-latitudes, and then up towards the poles. And by contrast, the global winds are also going to move the cold temperatures from the polar areas downwards as well, toward the equator. So the global winds you could think of as great transporters of heat throughout the world, like hands that nature uses to distribute energy around the world. On this diagram, you can see there are 6 major wind belts all across the world. There are really 3 that are a mirror image of each other on the northern and southern hemispheres. And that makes it much easier. You can see the northern hemisphere, you have the trade winds. They run approximately 0 to 30 degrees latitude. You have the westerlies, which run approximately 30 degrees to 60 degrees latitude. And then you have the polar easterlies, which run from 60 to 90 latitude. I say approximately because they migrate up and down over the course of the year, but that's basically where their neighborhood is. And then there's a mirror image in the southern hemisphere. You have the southern trade winds, the southern westerlies, and the southern polar easterlies. The same thing, just going the opposite direction, because the Coriolis effect turns all these winds to the right in the northern hemisphere, and it turns all these winds to the left in the southern hemisphere. Another thing that makes this much easier is that everywhere on this map where you see the red lines, the global winds moving, they're always following the same rule that we established, the pressure gradient. They're going from high to low, down the pressure gradient, from a higher pressure to a lower pressure. Remember that phrase, winds blow from highs to lows. So you can pick anywhere, but take a look at the trade winds. They're running from the subtropical highs, which is around 30 degrees, down to the equatorial lows. This ITCZ area here, it's called the equatorial low. So that's from high to low. Same thing the other way. Subtropical highs shoot out the westerlies. They head towards the polar front, which is also the polar low, around 60 degrees, highs to lows. And then the polar highs up here, where it's real cold, air has no ability to expand. It's so cold. Then it gets contracted, and then that high pressure shoots out towards the polar low. So again, highs to lows. Everywhere you look, all the red lines doing the same thing, moving from highs to lows. And there's another pattern we can see on here that makes it easier, that the highs and lows are alternating. So around the equatorial areas, you have the equatorial low. So around 0 degrees, and the next one, 30, is a high, subtropical high. Next one's a low, polar low, and then the next one's a high, polar high. So every 30 degrees, they alternate, lows and highs. So let's look at this cycle that drives global climate. It's called the Hadley cell, this yellow loop around the equator here that shoots out into the upper atmosphere. What is that? Well, basically, it's a convection cell. It's a convection cell where you simply have air rising around the equator here. Because the sun's direct rays hit around there, causes the air to rise most. There's evaporation, lots of water evaporating off the ocean. You get lots of clouds. That's going to give us our Amazon rainforest, Congo rainforest, all these rainforests under those clouds. And then the leftover dried out air after it rains is simply pushed along by more air coming behind it. And here it goes out, and it's going to fall down around 30 degrees. Okay, that's going to form our subtropical highs. So, and then the air makes its way back along the bottom of the Hadley cell. And that return trip is basically what the trade winds are. It's simply the return trip of air in the Hadley cell across the surface of the Earth back towards the equator region approximately. Okay, and this area where the clouds are going up at the very beginning has a name. It's called the ITCZ. We'll explain all those things in a second. I just wanted to give an overall view of the entire Hadley cell. So the Hadley cell is simply a convection cell. And what that means is these are found all throughout the world in liquids and gases and ovens and magma inside the earth, all kinds of things. It's simply any loop where something moves around due to a heat source. So when I was a kid, I used to sit in the classroom, and I used to sit in the back and lean my chair back and bounce it off the radiator behind me back in the 80s. And that was the heat source. I was too hot. I get burned sometimes too. And the air would rise off the radiator and hit the ceiling. And that heat energy would carry it up there, but then it would lose that heat energy by moving, because heat and motion are the same for gases. By the time it lost the heat out here, there's no energy left, it falls, and then it hits the floor and makes its way back across the bottom, back to the radiator. That's just a simple convection cell. So this guy's too cold, I'm too hot, and people in the middle are just right. That's basically what the Hadley cell is. It's the convection cell, rising side, just like the heater in the back of the room, falling side, the air that's no longer got the heat left to keep it up in the air. So it's important to realize that the Hadley cell has two sides, and we can think of them in our minds as like a contraption. Okay, this is an analogy for the Hadley cell. Imagine you have a device, okay, like sort of like a shower head. You know, you pull the shower head off, it's got that handle, and then it's got like the shower head on the end of it. You can do your thing and shower. But imagine that it's got a double end to it, where one end is a shower head on the bottom. So here's your handle. The bottom is the shower head. It makes it wet. Top part is a blow dryer. Okay, so one handle, blow dryer, shower head. So that's like the Hadley cell. The bottom of the Hadley cell is like the shower head. It makes you wet. Okay? It rains all over the place. Up here at 30 degrees, that's like the blow dryer. It makes it dry all over the place. Okay, so if you're under that, it's dry. Just to preview, this is why we have the world's biggest deserts, like the Sahara. It's under 30 degrees and around there in the middle of Africa, okay, because it's dry air falling onto it. It's why we have the Mojave, the Chihuahua, Sonora deserts of Mexico, stuff like that. The world's biggest deserts are under this dry falling air from the blow dryer. Okay, so you need to visualize that we have a dry falling side, like a blow dryer, and we have a wet rising side, like a shower head. And we can move that up and down throughout the whole year, because remember, the sun's direct rays migrate up and down 23.5 degrees either way from the equator. And so that's going to take our contraption, our double-headed device, and move that up and down as well. So all these weather systems are going to move up and down throughout the year. Let's look at that middle part, the Intertropical Convergence Zone. Why is it called that? ITCZ. Well, it's actually very simple. You can see it's right here between the northeast trade winds and the southeast trade winds. They're converging together. It's, just to be clear, it's not a front. Why is it just not called a front? It's not a front because a front is two different types of air, like cold and warm, or dry and wet. But these are both warm and they're both wet, so it's not a front. They're just merging together. Okay, so it's kind of like you have a highway or something with two lanes, and you have two on-ramps, one from either side. So they can just merge on the on-ramps into the same highway side by side like that. They can run together. That's kind of what's happening here. And they bump into each other, and then they go up together like that and form these Hadley cell this way and the Hadley cell going that way. So that's the convergence part. They converge into the same sort of road, so to speak. And why intertropical? Well, because it's in the middle of the tropics, the upper northern tropics up here and the southern tropics down here. And sure enough, it's intertropical. It's between those two. So the Intertropical Convergence Zone is a cloudy belt. Just to be clear, what they're showing us with this Hadley cell is all around the world, right? The Hadley cell is not just like in one spot like this, just to be clear. It's all around the world, like a ring. And they're just cutting away here, slicing away so we can see the inside of it, okay, in this picture. So I'll make that clear. So the belt of clouds is all around the world. You can actually see it from space. Okay, it's right there. You can see the ITCZ from space, and it's that pronounced. And it actually, like we said, the shower head and the blow dryer, they move up and down throughout the year. So this is the shower head part, right, the ITCZ. And you can see that has migrated between July, when it's highest, right, when the sun is at its highest point, most northerly point, and then it comes back by January, it's back in the middle again. So, and why? What about these bends? Well, the bends are largely due to the uneven heating of land versus the ocean. So land heats up much faster than water does. And so you can see where it goes over land, it starts to bend more to the north, further from the equator. And then when it comes to the water, it starts to bend down like this. Okay, so that's just a pattern. You want to see that ITCZ working from the side view up close, that this is a cutaway. So here's the band of clouds that's rising up in the middle where the two trade winds on either side come together, right? The Intertropical Convergence Zone is the convergence of those trade winds into the same lane, and they bump into each other, they go up together, and then all the rain falls, and then the leftover dry air slowly falls out at 30 and 30, north and south. Big loop. What about this other side of the Hadley cell, the blow dryer? What happens at the dry falling side up here around 30? Well, here comes this dry air falling down. Imagine you're standing there, or you're in a boat there or something, and it's falling on your head. It's coming vertically, directly down on you, right? It's not rising up vertically above you like zero. It's in the ITCZ, it's coming down on you vertically. So that air is just getting squashed as it hits the ground. Just like you dribble a basketball, when the basketball hits the floor, it gets squashed, right? It doesn't stay circular. It gets squashed under high pressure. The same thing, it's squashed air into the subtropical highs. That makes it under higher pressure. Okay? When you squash something, it's under tighter space and higher pressure. That's called a dynamic high. You become a high pressure zone by being squashed. It's also high pressure because it's cooler air. That's called a thermal high. So it's both a thermal and a dynamic high in the subtropical highs. So there's this whole ridge, basically, all around 30 degrees, all these subtropical ridges or subtropical highs. These go by different names around the world. Here's the Pacific High, the Bermuda High, just depending on where you are, these local names. And they're often called the Horse Latitudes. They're nicknamed the Horse Latitudes, around 30 to 35 degrees. The reason they're called the Horse Latitudes has to do with a legend of Spanish explorers coming to the New World. Remember that the falling air here, if you're in a boat, let's say out in the middle of the ocean here, and you're under the subtropical highs, that falling air is coming vertically straight down on your head, the opposite of the ITCZ, where it's going vertically up above your head. So that means that if you're in the boat, you're not getting any wind blowing your sails. There's nothing side to side, no horizontal wind that can take you anywhere, right? It's just vertical coming down on you, but that's not good. So you're going to get stuck. So the legend is that the Spanish ships would get stuck in these subtropical highs for sometimes months at a time in these calm, windless areas. And so they started running out of water, and they looked around and said, well, who's drinking a lot of water? And horses drink a lot of water. So they started throwing the horses off the ship. And they started throwing the horses off the ships because horses drink a lot of water. And so hence the name, the Horse Latitudes. So let's follow what happens to the air as it falls down into these subtropical highs, because that's actually what's going to give us our trade winds and our westerlies. Okay, they're both going to be air that's shooting out of the subtropical highs. Remember, we said winds blow from highs to lows, and high pressure areas, highs, are like pumps. The air goes out from them. Air goes out from them. Lows are like vacuums. Air goes into them. So here's a subtropical high right here. Air is falling down into it. It splatters when it hits the earth, whether it's the water in the ocean or whether it's the land over here. Either way, it's just going to splatter everywhere. Kind of like if you imagine you had the blow dryer, right? And you had all these, all this sawdust or something on the ground, and you shoot the blow dryer down toward the ground. It's just going to, everything's going to splatter in every direction. Or if you have a box of Cheerios and you hold the box up high, you dump it onto the floor, you just pour it onto the floor, it's just Cheerios is going to splatter in every direction. Okay. So here go the Cheerios. The air is falling down in the subtropical high. The westerlies, the Cheerios fly out this way. The trade winds are Cheerios flying out this way, right? It's flying out and it's turning to the right because of the Coriolis effect. And the westerlies, and it's turning to the right in the trade winds too. The same thing in the southern hemisphere, except it's turning to the left because they have a different direction for the Coriolis effect. Okay, so that's what's generating our westerlies and our trade winds. They're just highs to lows. They're shooting out of the subtropical highs towards the polar low up here. The polar front is a low. And they're turning along the way because of the Coriolis effect. Here's another view, subtropical highs. Here's the westerlies shooting out, turning to the right with the Coriolis, turning to the right with the Coriolis. The trade winds, same thing, southern hemisphere, except to the left. So let's get to know these trade winds. Trade winds are the prevailing winds of the tropics and also the subtropics. So tropics is 0 to 23.5, the Tropic of Cancer, for example. And then 23.5 to 35 latitude, that extra bit is called the subtropics. Okay, it's just outside the tropics. So if we add those together, right, the tropics and the subtropics, we get all the areas that the trade winds cover from 0 to 35. It's the most reliable winds for ships. It's the winds that blew Columbus and Balboa to the New World, the winds of trade, the winds of commerce. And they're the largest winds, meaning the winds that cover the most area of the globe by far, because the globe is circular like this, right? So that means that it's going to be widest around the tropics, right? The widest part of that globe is there, and that's where they are. So they're covering the widest, biggest area on the Earth's surface. And the trade winds, again, are just the bottom of the Hadley Cells. So the air goes up, it comes down, and then it has to make a return trip back towards the ITCZ. And that return trip is what all these red hours are doing. They're all just coming back to the ITCZ on the bottom side of the Hadley Cell. Just to be clear, we have an upper atmosphere, like the upper line of the Hadley Cell, the upper yellow line, and we have a lower atmosphere, surface winds. So upper atmosphere winds up here, and then surface winds down here, and they move in opposite directions. The surface winds go one way, and the upper atmosphere winds go the other way. So now here's something that might come up when you're looking at actual countries and you're trying to figure out how the trade winds affect their climate, because it can be confusing. The trade winds start out dry. They always start dry because they're shooting out of the subtropical highs, and the subtropical highs are just dry, cool, falling air. So they're always going to start dry because the subtropical highs are dry. But what happens to them depends on where they are, whether they stay dry or not. If they shoot out from the subtropical highs over the ocean, then even though they started dry, they're going to get really moist and wet really quick, right? Because they're running over this super hot ocean that's going to be evaporating lots and lots of moisture. Okay, so they're going to bring lots of moisture onto, say, Brazil right here and Venezuela along this coast, really wet, rainforest, et cetera, et cetera. But if the trade winds shoot out from the subtropical highs in Africa, in the middle of Africa, there's no water around, so they're going to stay dry across Africa. And that is going to give us our world's largest deserts. So if you look at this map here, notice that the Sahara Desert, the biggest desert in the world, and also all the other biggest deserts like the Arabian Desert, the outback of Australia, et cetera, they're all starting around 30 degrees at our subtropical highs. See, 30 degrees, and there they are. And then down here, 30 degrees. And then the trade winds blow out across Africa, and there's no ocean there to pick up moisture. So they just blow dry all across there. Okay, so you can just think, our device with our blow dryer, that's what's making the Sahara. That's what's making the outback of Australia, the great sandy desert down there. That's what's making the Namib and the Kalahari. Okay, other things too. Actually, there's a cold ocean current which also contributes to those African deserts. But basically, they're under the blow dryer. So, and just to be clear, in this picture, yes, there are other deserts outside, like there are cold deserts up in Mongolia and stuff like that. But that's for a different reason. There's at least 3 reasons to create deserts. Trade winds are also the winds that blow tropical storms, like hurricanes, that for us start off the coast of Africa and they blow from east to west towards the Caribbean. And sometimes they come up towards the east coast of the US, and sometimes they duck into the Gulf of Mexico. But the fact that the trade winds run from east to west, the trade winds are easterlies, is why the hurricanes always move from east to west. And that even goes for the Pacific, where hurricanes are called typhoons, and it goes for the Indian Ocean, where they're called cyclones. They're always moving from east to west because they follow the trade winds that carry them along. What about these westerlies? These are the prevailing winds of the middle latitudes, which is most of the United States, Europe, China, and they carry the warm air from the tropics out of the subtropical highs out across America, across Europe, across China. They warm it up. So this is going to have a warming effect on these middle latitude areas. Because they run from west to east, the westerlies are the reason why in America our weather systems usually travel from west to east. We usually get our weather from whatever's happening in the Midwest or in the West Coast. It slowly migrates across the United States to the east. The exception to that is in the summertime, like hurricanes, they're on the trade winds, and so they've migrated up for the summer. And so in the summertime, we get the opposite direction. We get storms from the east, like tropical storms, which come from east to west. The westerlies also blow onshore on the west coast and offshore on the east. We just look at the map, right? So from the west to east, that means that they're going to hit the west coast of the U.S. here, like California, onshore and coming onto the shore. But in Virginia and New York, they're going to be going offshore. And that has lots of consequences. For example, it blows waves much stronger onto the coast of California, right? Because the winds are pushing the water onto the coastline. Whereas on the East Coast, it's actually working against the incoming waves. And so it makes much weaker waves on the East Coast. And finally, we go all the way up to the top, the third set of winds, the Polar Easterlies. They are shooting out of the polar high. The polar high is a high pressure area that's created mostly by the low temperatures because there's such a lack of energy from the sun up there. So when air doesn't have a lot of energy from the sun, it can't expand and it gets tighter and tighter and tighter and under higher and higher pressure. And it wants to release to a lower pressure area. Out here at 60 is the polar low. So we have winds blowing from highs to lows up there. And again, they're turning to the right, the Coriolis effect. The polar easterlies, you can see here, they are going to collide with the westerlies. This is a front because the westerlies, remember, are tropical air that's moved outwards. This is polar air that's moved outwards. And so those really are different types of air. One is tropical and warmer, one is polar and very cold. So whenever you have two different air masses on either side, the surface or edge where they meet is called a front. And that's what the polar front is. It's the surface or edge between where the westerlies with the tropical air meet the polar easterlies. And that polar front, as we said, is a polar low. It's a low pressure zone. And like all fronts in general, that's where storms form. And in this case, they're often cold storms in the wintertime, like blizzards. So if we have a lot of snowfall or a blizzard even over you in the wintertime, you're probably somewhere around the polar front. And these major winter storms that form along the polar front are these circular loops similar to hurricanes, except just much colder. But the form of it, the spiraling of it, is similar to hurricanes around a low. And that's called a cyclone. Okay, a cyclone is a spinning storm around a low. We'll talk more about that later in the storm section, but a hurricane is a higher level of tropical cyclone. And you also have extratropical cyclones, meaning cyclones that form outside the tropics. So in this case, along the polar front, you get what you call midlatitude cyclones, like a blizzard. So this map shows the polar front, but how it moves throughout the year. So in the wintertime, it's way down here. And the summertime, it's way up here. And remember, the polar front on the right is where the westerlies meet the polar easterlies. And so remember, the westerlies in our wintertime in the northern hemisphere, they're pulled down as the Hadley cell moves down. They go down too. And that allows the polar easterlies to come down much further. Okay, so in the wintertime, here's the polar front way down here. That means that the westerlies have receded back behind it like this. But the polar air from up here can extend all the way down, for example, over Virginia, the Carolinas, et cetera, here, all the way down here. And when that polar front passes over your head, your day-to-day weather changes enormously. So if you're on the southern side of the polar front, it might be 70 degrees. And then that polar front passes over you. And the next day, all of a sudden it's 30 degrees. That's why we have some wacky weather in the wintertime, because that when that polar front is moving back and forth over your head, you're actually changing from being under the westerlies or tropical air masses versus polar easterlies, which are much, much colder. And again, when the polar front is right above you is when you have your snowstorms. And by contrast, in the summertime, that polar front migrates very far north. So all that polar air is pushed up high, and we get the tropical air masses coming out with the westerlies. They're the ones covering the vast majority of the United States. So it warms everything up. So in the big picture, places that have very unpredictable weather that changes a lot day to day tend to be places that are under the polar front a lot, where the polar front keeps passing back over them again and again and again. For example, Chicago here, that place kind of right in the middle. So the polar front will come over them and back, over them and back. Sort of like if you have shades on a window, and then the bottom of the shades, the edge of the shade, there's a little handle you pull, a little string, you pull it down. So if you imagine that shade is like the polar air, and then below it is all the warmer air, from the westerlies, you can keep pulling that shade down and bringing it back. So every time it passes over and goes back, the weather changes from warmer to cold and back and forth. Last but not least, we have the jet streams. Jet streams are sort of like superhighways of air, very strong, very narrow bands of air that shoot along at super high speeds, 250 miles an hour or more, at about 5 to 9 miles up in the atmosphere. So you can see there's a polar jet stream and there's a subtropical jet stream in both hemispheres, and all of them move in the same direction. All of them move from west to east. And the jet streams are like railways for storms, so to speak. They carry storms along. So if you want to know if a storm is coming, you can see, am I sort of in the path of the jet stream? Is it going to carry that storm to me? So storm tracks or storm paths often follow the jet stream. That goes for the subtropical and also the polar jet stream. The polar jet stream is basically above the polar front, and the subtropical jet stream is basically above subtropical highs. So in general, if you want to see where the storms are coming in the wintertime, who's going to get snow next, you can see, okay, where's the polar jet stream and who is sort of in its path, because the polar jet stream will carry that storm across the United States. And the places that are furthest away from it are going to have the least changes in weather. So that's a look at the global winds. What are the most important ingredients in creating global climates? As we go forward, it's going to be very handy as we see how all these ingredients come together to make the stew that is a climate in a particular place.